With that, we're going to move into Dr. Boutt's updates, and looking forward to that. Dr. Boutt?
Awesome. Thank you all. And it's been an exciting 3 months. As you can see, we have a new team member on the team, and Rachel, and we've I think accomplished quite a bit in the last 3 months. So what we would like to share with you tonight, so it'll be a bit of a tag team presentation. I'll kick things off, and then I'll pass it over to Xander, and then to Rachel, and then to Brendan and Carly. But we just want to cover some of the main highlights of what we've done really since last, I guess it was late November that we last got together and chatted. So we're going to really first start with some of the updates to the mod flow model, the density dependent model. That this is the tool that we use to make predictions and assessments of the interaction between fresh and salt water. And we have some exciting graphics and developments to share with you. Then we're going to talk a little bit about some of the work that Rachel has spent the last month and a half looking into, which is taking a fresh look at the subsurface materials within the Plymouth Carver Aquifer. And believe it or not, it's not all sand. There's lots of different geologic units in the subsurface, and they will play a very important role in how fresh water and salt water interacts. And that will be followed up by some discussion of an assessment that Carly has led with Brendan's assistant, looking at the salinity distribution in the aquifer. And there's some new results that I won't give away. And then finally, kind of following up on what Dodie had kind of referred to a little bit, we could use a little bit of help from you all in taking a look at what the town has kind of, what some of the projections might be for the town in terms of water use going out into the future, and thinking about how we can incorporate some of those water use scenarios into the modeling, because freshwater pumping of the aquifer is a really important stressor on the dynamics, and we should definitely discuss as a team, how we want to envision those different scenarios. So you can all see my screen, okay? Awesome. So we're kind of here at in this kind of work package 3. Xander has just finished some of the density dependent groundwater flow models for the Plymouth Carver system that we'll present tonight. And we're about to move on to some of the scenarios, looking at projections of both the impact of sea level rise on the dynamics of the freshwater saltwater interface, as well as different scenarios of essentially terrestrial changes in precipitation, changes in hydroclimate that also will impact how the hydrology of the system works. And so we're on target, and we're on target, Courtney, too, I think, to use all the funds. So that's a good thing, and to take advantage of all the match that you've all provided, and I think that really deliver some really helpful tools and assessment for the region. So where we are is we've looked at to date, looked at where the freshwater surface water interface is. We've refined the hydrogeologic model of the aquifer system, and we've updated the existing groundwater flow model. In year 2, our focus has been looking at the relationship between the different surface water features and the freshwater and saltwater mixing zone, the interface that we're kind of focused on in terms of saltwater intrusion. And we're currently in the middle of assessing the certain dynamics that are at play in this sole source aquifer. And then finally, we'll reach some, I think, important recommendations for future work and future assessment. I see somebody put something in the chat and I can't quite see that. Let me see. Okay. You're welcome, Courtney. All right. So, again, just to kind of bring everybody up to speed, what really we've been focused on is developing a tool, this groundwater flow model that allows us to assess the interactions between freshwater and saltwater in this coastal aquifer. As you all know, the questions around the saltwater or sea level rise and how saltwater will intrude the aquifer is really important, not only for drinking water quality, but also how the aquifer interacts with different surface water features such as the ponds and the streams that you all care about. And one of the things that we're trying to do and really pushing the envelope on is to use different understanding of how sea level might change into the future, and then incorporate those into different assessments of how the aquifer will respond to those changes. So with that, maybe Xander, are you there somewhere?
Yeah, I can jump in.
All right. I'll let Xander jump in. This is a little bit of a recap from last time, just to orient you to the model domain. And again, we'll get pretty technical here, and I would really encourage you all to just ask questions, raise your hand, and we'll take our time going through this.
Yeah, thanks, Dave. So this slide has some animations involved in it, but we're just looking at this this figure on the right. You can see in that light blue outline, that's the existing USGS groundwater flow model from 2009. And this slide just kind of describes how we built our model domain, which is in purple. So if you look at that, that color map within the blue line, you can see that that's showing the water table elevation. And what we did is we basically, some of that water is flowing west and some is flowing east. And we made our model domain right at that groundwater flow divide. And then you can do a couple animations, Dave. And then one more. So you can see so we set our western boundary at the groundwater flow divide, and then the eastern boundary we extended 10 kilometers offshore.
So the important point about this is that we're able to save some computational effort by not simulating the whole aquifer domain. Some of this water, flows down the Buzzards Bay and other drainages there, and really focused on the interaction between freshwater and saltwater along this part of the Cape Cod Canal, as well as the Cape Cod Bay.
So here's just the domain one more time. You can go to the next slide, Dave. And so here is what the model looks like from the side. So on the right side, that is the coast. You can see it's a lower elevation, and on the left side, that's towards the land surface. and the top of the model is just the top of the land surface, and the bottom of the model is basically the bottom of is the top of the bedrock. It actually extends 15 meters into the bedrock. And you can go one more slide, Dave.
Yeah, just so people understand. So this is like a section into the earth. So this would be the land surface and then going down into the subsurface. So this would be the model domain, and Xander, this is offshore, right? This part?
Yep, that's kind of like that's offshore. You can see where it slopes down to offshore.
Okay, so this would be like the land surface here?
Yep.
Something
exactly.
like that, okay.
And so just to kind of zoom in a little bit on this model from the cross-section view, you can see that between 8 and -32 meters above sea level, we made the vertical discretization about 4 meters. So then we really want to know what's going on in that saltwater intrusion zone. So that finer discretization will allow us to do that, which will be important.
So just so people understand too, is what this means is essentially what we do is we split up the earth into chunks, and within each one of these little boxes, we make predictions of or assessments using physics, using the law of physics and conservation of mass and all those things. What is happening between the freshwater, which would be here in this part of the aquifer, and the saltwater here, and resolving the position of that interface is critical, because really we're talking about, in many instances only, a few meters of sea level rise, or a meter, if you will, and trying to understand how that's moving into the subsurface requires some, more resolution of what's going on.
So, so here's just some kind of initial results from the model. So this is a map from bird's eye view on the left, kind of the color map showing the water table elevation. So you can see in red, that's a higher elevation, and in blue, so it goes kind of red, yellow, green into blue, and blue is just the elevation of the ocean, so 0 meters above sea level. And then if we jump over to the plot on the right, you can see on the x-axis is the simulated head, so that's the water elevation that our model predicts, and then on the y-axis is observed head, and that is the water table elevation that's actually measured from a well. So it's the actual groundwater elevation. You can see they follow a linear trend. And this is before really we calibrated the model. So the goal of calibration will be to basically take all those blue points and have them fall onto that black line, because that black line is the one-to-one line between observed head and simulated head, meaning that all our simulated heads match exactly to what the actual water elevation is.
Xander, can I ask you a quick question about the layering?
Yep, of
simple
course.
question. Are all the layers confined, unconfined, or just is the top layer unconfined? How did you specify the layering?
Right now, they're all unconfined.
Okay. All right. That's great. Thanks.
Yep.
Yeah. So just, I think, Xander, you explained that really well. And just to reiterate, if the model was perfectly describing the aquifer, all these blue points would fall along this black line. This current model, the results that are being shown here, is not adjusted to, or that it's a single property model. It has one hydraulic property. As we'll discuss in a minute, we're working on revising the geologic layering within the model that will allow us to better simulate the the actual conditions of the aquifer. So the goal with any model is not perfect, and the goal is to try to best capture what's going on in the aquifer with kind of the least complicated model that you can have. Hopefully that explains things. So this is just an example of kind of the process by which we would end up at a model that would be as good as it can be, you know, with the resources and tools that we have. Does that make sense to y'all?
Yes, it does.
Okay, awesome.
Thanks, Dave. So now kind of switching from the water table elevation, we're now looking at the bird's eye view of the model again, but of the salinity. So the red in this is saltwater, so it's 35,000 milligrams per liter, total dissolved solids, and then on the left, that's just fresh water. So let's take a look at it from the side angle. So this is the same cross section we were looking at before when I was describing the model, and you can see here the interface between the seawater and the freshwater. So once again, the seawater is in red, and because it's more dense, it comes underneath the less dense freshwater. And yeah, so I think this is a really good interface. It looks realistic, so it's promising.
Yeah, and so this, I mean, one of the good things is to even get to this point. It took, you know, these are very complicated models, but you know, we have the boundary conditions working right, which basically just means like how the model is being driven by changes in the amount of fresh water that's coming in. And so this is really the building point to then start assessing you know, how saltwater or how sea level rise will impact saltwater migration into the aquifer. So yeah.
Yeah, Xander and Dave, what's the profile of this cut with the high point there? Where are we looking, east to west, north to south on the cut?
Yeah, Xander, where would that?
So this is
be?
literally what this cut is actually looking directly north.
Oh.
So that interface is actually at the canal in the south.
Oh, okay.
Yep.
Oh,
So it's actually not a cut through the model. It's actually just but if you were to cut through the model in one of the southern parts, it would look similar to that, which I have done.
So wait a minute, does it go this way?
Yeah, we'd be looking north.
oh no, is it an east-west section or a north-south section?
East-west.
East-west
East.
looking north.
Yep.
Got it. Okay, so it's down here.
Yeah, it's looking northeast.
Oh, looking north. Got it. Okay. Sorry, I confused myself. Got it. Okay, so we're like basically we're looking here.
Because you can see on the bottom left, it's like literally perfect X, Y, Z all lined up.
Got it. Okay. So
Terrific.
this would be the like Pine Hills here.
Yep.
Okay. I see. We're looking almost obliquely at it. Okay.
Yep.
And
Awesome.
it looks like there's some of the bedrock, the bottom layer has, you know, salinity predicted in it, but is that, I know this is just initial runs, but I don't know if it's supposed to be there or not, or what.
Yeah. To that, I'll say and Dave might have something to add to this, but so right now this is a homogeneous model. So right now there's no actual, like the bedrock doesn't have a lower hydraulic conductivity right now.
Uh-huh.
So with a lower hydraulic conductivity in the bedrock, there's a chance that there's less salt water in the interface or in the bedrock, but I'm not entirely sure.
I'm sure it'll work out once you guys start working with it more.
Xander, the initial condition was the model or the subsurface was full of salt water. Is that correct?
No, that it had 100 milligrams. It had no salt water.
Okay, so this salt water migrated to this low point.
Yep. But this is where it gets tricky because it's looking in that really weird direction.
Yeah.
So
I know.
that, so that stuff, that low point right there. Sorry, if that's what you were talking about. Sorry, I misunderstood the question.
No, that's just what I was looking at, but
that is actually like connected to the ocean. It's just like it's the deepest bedrock, really much farther north.
Yeah, that's approximately in the location of Buzzards Bay.
Okay. Yeah, I mean, if we had the section line on there, we'd understand it, I'm sure.
yeah.
Yeah.
But I mean, one of the things I think that illustrates is that, you know, especially when we start looking at different scenarios with freshwater pumping, you know, the aquifer somewhere at depth is saltwater, even below, you know, even in some of these areas. So it gives you some perspective on the interaction between the less dense freshwater, as Xander mentioned, and the more dense saltwater. And so for every, let's say, meter change in in the water level of the aquifer, there's going to be a fairly significant lateral migration, or can be a significant lateral migration of the interface, and that's kind of what we're after in these simulations. Xander, this is Xander's baby right now. So anything else you wanna add to this?
No, nothing else right now.
Okay.
I'm excited to get those simulations running and get some results back to you all. I'll say that.
Yeah. So we're right. I mean, this is kind of an exciting. The next month is going to be really interesting in terms of putting the different scenarios into the simulations, and we've got a couple other things that we want to tweak in the model so that we can get it, get it to the point where we can start to communicate some of the results.
Yeah. So I guess we've kind of said these things, but basically we've finalized the grid. We've finalized the density dependent model, and the next steps are really just to run those climate change simulations.
You guys mentioned that you are going to be adding, you're going to take it out of a homogeneous model and put in spatial variability of sedimentary texture, heterogeneity. Is that part of what you're doing now?
Yeah, exactly.
Nice.
Peter, as usual, a very appropriate question, because we're going to talk about the stratigraphy now.
Awesome.
Yeah. So Rachel, I'll let you go with this, and then I'll be here to advance the slides.
Yeah, sounds good. Thank you for the update, Xander. So what I've been working on for the last month or so is just characterizing the hydrostratigraphy in the aquifer area. So what I've mainly been looking for is confining units, specifically clay, silt, fine sand, silty clay. And so reading all these different reports going back into the 90s, there has been existence of a confining unit, but it's not very clear on where it is, how large it is, how far onshore it is, if it even goes onshore. So just looking into these different reports and well cards, we've been able to characterize that a little bit better. And just an example is this cross section from 1992, just showing silt and clay from offshore to the Plymouth Beach area. Yeah.
Yeah, and so Rachel, I'll just add to that too, is just so people understand, a confining unit is a term that we use in hydrogeology to define a layer that is less permeable to groundwater. So what that means is that it's harder for the fluid to move through that material because it doesn't move the water as easily. So in this particular case here, this like the original model by Hansen and Lapham that was built for the Plymouth Carver, the USGS drilled 2 wells that penetrated actually almost 100+ feet of low permeability silts and clays that really could impact how the saltwater freshwater interface could move through this material. And so we probably spent more time on this than originally we had budgeted, but it's really important to understand where these units are and where they're not, because it's going to impact how we predict the movement of the freshwater and groundwater compared to the homogeneous or constant hydraulic property model that Xander just showed.
Yeah, thank you, Dave. So this is just another cross section from a different part of the model in Pine Hills. So this is from, I think, 1998, and this is just from water supply exploration. And if you look at the purple unit in the middle, that is just the confining unit in between 2 sandy layers. But as you can see in this photo, it says silt, clay, sand. It's not exactly clear which confining unit is laying there, and just moving forward with wanting to find out more information about these units and what they would mean for the groundwater flow and the aquifer as a whole.
I'm curious. Oh, sorry.
Go ahead, Peter.
I was gonna say, I'm curious how you guys are organizing all this data that you've got. You've got these cross sections, you've got well logs, and you've got budget limitations. How are you guys like maintaining all this stuff in either in your own minds or on the computer?
Yeah, so I guess just getting into my process of how I ended up creating a map of the confining units was there was a gap of data in Plymouth specifically. We got a lot of wells in Kingston and Duxbury, but there was a lot of well cards that needed to be gone through. In Plymouth specifically, there's like 2,500, I believe. And so this is an example of one of the better well cards that had location data, as you can see in the blue. It had coordinates, and then it had pretty clear lithologic data at the bottom. This well card had silty clay and silty gravel, so I was basically just making a master Excel sheet noting where these wells were and then which units were there. And then creating the map, I would choose either the thicker unit or the one that I would consider more confining, whereas clay, since the water would move, it would be more of a barrier compared to fine sand. Clay would be noted for that area. And then that is how my process was to create these maps. And then this is also combined with compiled data from Mass DEP. So there's 115 wells with confining units from the EEA well cards, and then there's an additional 183 geocoded wells from Kingston and Duxbury.
So have you all looked at the exploratory wells that were drilled over the past roughly 15 years, 20 years down into the aquifer to good depth? for town purposes for siting of the public water supplies.
Yes, yeah, and that's informed, part of that's informed in some of the wells, and one of the things that we know from the region of downtown Plymouth is that there is a pretty laterally continuous confining unit there from those particular holes. And then we've augmented that with different pieces of information. We've interacted quite a bit with Neil Price, who's at Horsley Witten, who was the chief hydrogeologist on all the Pine Hills exploration, has also worked for the town of Plymouth. And one of the things that we've been trying to determine, as Rachel will show you in a minute, is this cross section here is from central Plymouth, so to the south, right, of downtown, and it shows a confining or a lower permeability horizon at sort of similar depths than you see into the north. And I've been asking Rachel this question constantly over the last 6 weeks. It's like, how laterally continuous is this unit? Like, do we see it all across, the aquifer? Does it reflect a time when there's a glacial lake called Glacial Lake Cape Cod that sat in this area? Does it reflect when the glacial lake came on shore and deposited these these clays and silts? Or are what we are seeing is a like localized pockets of silts and clays in let's say ponds or kettle ponds like we see on the surface today, and it's just this hodgepodge of these units. So yeah, Hampton, we've looked at those records. We've as Rachel was communicating, these well cards she was referring to are drillers, what they're drillers logs. Sorry, I think that's a
Oh, we're losing you, David. I can't hear you.
okay. Can you hear me now?
Yes.
Okay, sorry. My phone was just going off. So these are some of the well cards that Peter and Hampton and folks helped us bring in, as well as we've been working with Mass DEP in particular to help geocode or geolocate additional geologic data. And what that means is we had information about the subsurface, but we didn't know where these wells were located. And they have a team of, 4 or 5 staff that have been helping us try to figure out where these holes are, so we could spatially locate them.
Nice.
I will say that your team, Dave, has got the patience of Job.
Yeah, I mean, Rachel, like, seriously has been working on this since early January, I think.
Yeah, right after Christmas.
Yeah. So yeah, and the cool thing is I'm really excited about this because I think it's really going to help us really improve the understanding of what's in the ground, that in a way that hasn't been looked at before.
So this is the map that I came up with based on all of the data from Mass EP and the data that I had collected from the EEA well cards. From how the geologic findings, it indicates that there's more confining units in the north of Plymouth Beach. They, as you can see at the top of the map, there's definitely a denser variety of them compared to in the south. I also just found it interesting that it was kind of varied confining units. It's not just clay, it's not just sand, and that's just indicated by the different shapes. I know it's a little hard to see with like the large coastline here, but and then the gray like shapes on this map indicate non-confining units. So within those well cards, there was also just coarse sand and medium sand and gravel. So I also noted those units, but it just shows that we were considering other units as well. But I feel that the correlation in the north is something of interest and something that we are hoping to look a little bit more into in regards to the model.
I think it's worth noting that there are some wells, since I walked around and knocked on a lot of doors in the Ellisville area, there are some wells where there's definitely perched water on something, likely clay, above sea level. So I don't know how many of your logs, show that confining unit, and the confining unit might be, high enough up that it's above sea level anyhow. And, it's maybe causes perch conditions on top of it or something that doesn't matter that much. But yeah, I definitely noticed some wells that indicated there was something holding the water from going down to the sea level aquifer, but didn't have any drillers logs to look at the textures.
Yeah, and so in this map that Rachel made, is the colors correspond to the top elevation reference to sea level.
Oh yeah.
So we see that, I think that those observations are consistent with some of these points. We'd have to go and look at, like, for example, this yellow point here, this other point in here. I would hazard a guess that, like, in this area, Peter, we actually have some evidence that those systems are perched, or at least above sea level. So what Peter is saying is that low permeability layer holds up the water, and it's above sea level. And in the modeling, Dan and Xander and I have talked about this quite a bit. As far as the saltwater intrusion problem is concerned, those areas are going to be pretty isolated from effects because they're above sea level. But it's really, I think what Rachel has found here is really compelling, of a pretty laterally continuous low permeability layer in the subsurface, at least in the north, probably north. It's an important feature, obviously, the Pine Hills is, and there's some geologic evidence that there might have been a kind of a glacial lake, essentially a glacial lobe that would have of ice that would have come down, retreated to the north, and left a depression north of the Pine Hills where this sediment accumulated. So that's something that we're exploring that hypothesis, and we're going to incorporate that into the models.
Just so everybody knows, like, glacial sedimentary processes are very complex. A glacier can be dumping water into a lake in front of it and then advance on top of that lake. It can scrape away sediments. It can recede and there'll be more of a lake, and then something breaks through and it all washes away. I mean, it's very complicated, and can lead to a lot of subsurface variability.
Yeah.
Sounds like you're advocating for travel to Alaska and Patagonia.
Yeah, I mean, I did my master's in this stuff. It's a long time ago, late 90s. It is complicated. And one of the other things that adds to the uncertainty here is the quality of the information that we're working with. These are not descriptions made by geologists in most cases. They're descriptions made by drillers. A lot of times drillers, their number one goal is to not work, to do anything, you know, it's like they just try to get stuff done, right? You know, and you know, I think a lot of these areas where Rachel has identified as like kind of no confining unit, you know, we have to really be, it's hard to rationalize a geologic process where you would have this cluster of, let's say, silts and clays, especially 40 or 50 feet thick units, and right next door there's nothing. It's hard. So we're gonna one of the next slides we'll quickly discuss some of our different options for incorporating this type of information into the model, because I don't want to take, Cheryl, I know you told me 30 minutes and we're going later. I'm sorry. Rachel, is there anything else that you wanted to say about this?
No, I think you went through pretty much everything. Yeah, so I guess just discussing the next steps with this, and maybe Xander can talk a little bit more about the model, or Dave, but talking with glacial geologist Janet Stone, she did a wonderful report about Cape Cod in 2019, and just learning a little bit more about the existence of a northern confining unit and how it goes on shore, and just the overall glacial history of the area. We also plan to receive about 100 more geocoded wells from the Mass DEP, and just seeing where those lie in Plymouth and surrounding areas.
Yeah, and just this was part of this glacial lake complex that I was referring to here, and this, it's very, very difficult to explain a 50 or 60 foot accumulation of silts and clays without a long-standing water body there. Essentially, you would need a large lake that would have been there for a long time. And so one of the ideas is to try to take the mapping that Rachel has done and try to put it together with some other geologic pieces of information that are out there. So stay tuned on this. Hopefully by the next, by end of March, we'll have it all figured out, right, Rachel?
Yeah, definitely.
All right. So maybe Xander, you can kind of walk us through these two options.
Yeah, for sure. So kind of the plan is to basically see how this confining unit that we've been discussing, it's the key word of the last couple of slides, how this confining unit is going to impact saltwater intrusion. So the two ways we're going to do this is we're going to, so there's kind of one idea where that the glacial lake was really only in the north. And so the location of the lake basically determines where that fine sediment is, because it's deposited from a lake. So that blue line shows kind of one model simulation, which is going to just have the unit in the north. And then just to kind of see how the model would react if it extended along the entire coast, you can see the orange polygon. So we're going to do those two simulations, one just in the north and one along the entire coast, to see how this low permeable unit will impact saltwater intrusion.
Yeah, and thank you, Xander. And I think that the idea here is to, because we're never really going to know without additional geophysical surveys, which we have some ideas for that if you were able to come up with some additional funding. But we're never really going to know exactly where that unit is. So we will look at a few different scenarios of where the unit could be, where this confining unit could be, and look at how the model or the predicted interface might change in response. So we'll use these as kind of examples or end members of where that unit is. I noticed somebody's in the chat.
Peter is
Okay.
giving us kudos for the
Oh,
unfair.
nice. Yeah. Yeah, I mean, you can see, I mean, anyway, there's lots of uncertainty in these systems, so we're trying our best. Okay, so we're gonna switch gears a little bit, and I don't know if Carly's gonna lead this or Brendan, or we'll just choose.
Yeah, Carly, if you want to just talk through it generally, and I could just jump in, just basically just what we did and then some of the initial findings and stuff. Yeah, we don't have to go into detail about interpreting too, just, yeah. Cool.
Okay. Yeah. All right, so we began by extracting the water quality data from a couple different websites. These websites include the USGS, NIWIS, Mass DEP, Drinking Water, the UMass Acid Rain Monitoring Program, Cape Cod Rivers Observatory, and the Tidmarsh Living Observatory. And then we used the date range of 1980 to 2022 for our water samples. We then separated the data into 3 categories, and those categories are groundwater, surface water, and public water supply. And we're focused mainly on fluoride, specific conductance, and total dissolved solids as our parameters. And so each site typically had multiple recorded concentrations. So we calculated the averages based on the parameter at each site. And then we mapped them into ArcGIS. All right. So the first map here is showing you groundwater TDS variability, where high TDS is shown in the pinks here in the north, and in the east and west, and in the south. So I kind of assume that these areas are highly developed, or there's a high density of roads here. So this is the high TDS might likely be from road salting in these areas. And then the lower concentrations are in green, and that's where a state park is. So assumingly there's no road salting there, and that's why there's low concentrations. The Kingston area is experiencing some high TDS concentrations over here. And if you go to the next slide, you can see that in the surface water, the TDS is low. And this is represented by the green. We're thinking this possibly may be some sort of saltwater intrusion in the groundwater.
Yeah, potentially. Yeah. So I can just jump in, credit.
Yeah.
That's great. This good, really good work. What was this, like 1,000 groundwater sites, or how many sites are actually in the database now?
There
Like,
are,
after filter.
I can look very quickly. There's a lot of sites that we collected data from.
Yeah, so we had to clean it up quite a bit. There's a lot of different data sources and different qualities. So this is essentially a culmination, of the reliable data. And so that's what you're seeing here. And each of these sites has a lot of individual points. And yeah, so like Carly was saying, there's some interesting trends here. I think that the King area right by the coast is quite interesting, considering the surface water is low relative to the surrounding area. So that could be some potential hotspot area to look at. And yeah, and obviously road salt has an impact on the surface water, you can see there's hotspots in the surface water and probably in these wells as well. But yeah, and so we have this database, and there's a lot we can do with it, I think. So I sort of the idea would be to try to leverage it to do additional investigation. And yeah, so
I mean, I think there's some really interesting trends here. I mean, one of the things that just based on the observations is we don't have a lot of coastal, groundwater observations. I mean, I think that's, like thinking about that. The other really interesting thing that I see here is that, especially in the groundwater, in and around Plymouth, Plymouth, Kingston, is that there are higher concentrations there that may be co-located with where those confining units are. Do we have we have the public water supply here too?
So this is chloride. Yeah.
This is chloride. Okay. And this is one of the town wells here.
Yes.
Yeah. And that's one of the highest, highest concentrations of chloride. And then I don't know, Peter, what site is this? You know better than I do.
That, could be one of the production wells near Savory Pond.
Yeah. Is this
I'm trying
orange
to-
line is 3A, right?
Yeah.
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 So
I'm not
it
sure.
must-
Yeah.
This is probably, I don't know. We'll have to look at that.
Because there are two production wells down there, and there was also the Cedarville well, which I don't think is being. There are some issues around Cedarville, I was told. There was an old landfill there. I think it was about the landfill, not about intrusion.
Yeah.
Yeah.
There's obviously could be multiple explanations for some of these things.
Yeah. I was going to point out, but now you're showing a map of chloride rather than TDS, because up here in these parts in the Pacific Northwest, we do have some hardness issues that are not related to intrusion. And we have relic seawater or relic salinity, that just hasn't been flushed out of the aquifer since the sediments were deposited underwater, maybe under seawater in some cases. Sometimes we will try to correlate water level elevations with salinity to see if intrusion is whether you can implicate intrusion, because if the water level elevations are so high that intrusion wouldn't be happening, then you're kind of left with other explanations like relic seawater or relic salinity in the aquifer.
Sure.
Yeah, and looking at some ratios of some of these ions too, we could, if we find spots that we want to look at more, we can look at that too. That's a good way to sort of split up the road salt versus seawater. So
on the road salt and town wells are typically on town property, and as a result, I would check for parking lots where, for example, school bus parking might be a point of impact on one or more of the town wells. You drive the school bus on salty, sanded roads, park it, they melt during the warmer part of the day, and you might get some elevated chloride as a result.
Yeah.
Generally
Generally
speaking, the ones away.
Go ahead.
Sorry, Dave, go ahead.
I was gonna say, generally speaking, these concentrations are fairly low. Relative to seawater. And in terms of the relic seawater, I mean, most of these sediments are deposited in glacial freshwater systems or in freshwater glacial lakes.
Mm.
So
Mhm.
I think in this region we can kind of rule that out. And and one thing that I think will be one of the recommendations is to add additional or expand salinity measurements and key wells or key locations adjacent to the coast. So as you can see, there's not great coverage.
Right.
Yeah, we're trying to help on that, but maybe by the end of next summer we'll have some better data for you guys.
Yeah. Well, we'll do what we can, and again, as we say in this slide, we'll use that to try to calibrate the model again. But these concentrations are fairly low, and even in the model that we're developing, we're not going to be including salinity sources from non-saltwater sources. So
yeah.
Okay, I think we should wrap this up, Charles, because I'm sorry.
No, we wanted to hear the.
But
all
one last thing, I guess, Brendan, can you just quickly
articulate
in 1 minute, just articulate the ask.
Yeah, so Masterson used water use, water pumping from town production wells and commercial and irrigation to put into their model. So we want to do the same, but we want to update it because those are from 2000, 2005, and they only go up to 2030, which is obviously pretty soon now, actually. So if we can, we would potentially, an ask would be to try to compile water, so extraction pumping rates from the towns. I think so the town production wells particularly, but also commercial properties and irrigation within those towns. And we actually have, our model is slightly smaller than Masterson, so we have less, which is helpful, less towns. But we would, if we can get like what the rates are now, and then potentially an estimate for, let's say, one time period in the future, and we can try to project those rates to the end of the model, run. So 2100 preferably, that would be great. We can use monthly rates, and we can simulate this extraction into the future. Yeah. So I don't know if that's.
Let me just clarify a few things. For example, this figure is from the USGS model report that shows an increase in the amount of groundwater pumped in 2030 compared to 1985 and 2005. And we were wondering if anyone in Plymouth or the surrounding communities has some idea or knowledge of any water use assessment or projections into the future that could help us inform, should we just flatline after 2030? What's the town of Plymouth planning for in terms of, water demand, and population growth, essentially.
So Peter, does Eric's report have any of that in it?
I don't know. I mean, there are a number of players at the town of Plymouth that I've interacted with. And David, I had told you I was going to try to get you in touch with Kim Tower, but she's been ill, and I think she's back. So this is a good jingle for me to actually reach out to her. I want to see how she's doing anyhow. But she's not the person who would have the projections. It would be the folks in public works like Sheila what's her last name?
Scarzy and Peter Gordon.
Yeah, I mean, she might be able to help. If you guys are connected and she's excited about this model, which she should be, and I will communicate my excitement about it, then she can maybe help you get that data from those guys. So I guess that's what I can offer, is to talk to Kim and see if she can make a connection with Public Works for you guys.
And that would be great. I mean, if, again, what we're looking for are some idea of what the town or towns in the region are thinking about in terms of water demand, going into the next 20, 30 years and beyond.
I've got a spreadsheet that I'll share with you, Dave, that's got it's a projection of the it's got historical information in it and the population projected growth out into the future. It's a log linear plot, and it's the reason that I raise it is I've got some significant confidence in it, because if you look at population all the way back to when white people set their feet on this ground, you're got a 0.95 is the R value. So it's about as linear as I've ever seen in population growth, and it gives a sense of where we're going to be if we just continue along the same rate of growth that we've shown over the past several centuries.
Yeah. Okay.
There has been some planning. There's a planning document that is at least 4 years old at this point that was in draft, and I don't think it was ever finalized.
It wasn't.
And but I mean, they certainly react to the fact that we're going to run out of water, so they must have some projections to back that up.
Yeah. Okay. That's exactly what we're looking for. That would be great. And who could get that to us? Or
I believe I have the draft, maybe, that I reviewed, and I don't know if they ever made another draft from it. I can definitely send it. Yeah,
it's certainly on the town webpage.
Oh, is it? Okay.
Yeah, the 2019 draft plan is on the town webpage. If I was just looking at documents within the past week or so, and I saw it out there.
Okay, so you could send a link.
Yeah,
that would be great. I mean, one of the things that you should all know, and I think you probably understand this, is most of the water that's pumped out of the aquifer is returned. So, but what matters is where it's pumped and where it's returned. So, in the Masterson model did a nice job of quantifying that. That will be in our models. But if you're pumping a lot of water in one area and returning it to another region, through either leakage or focused infiltration, that's something that will definitely impact the dynamics.
You guys mentioned some climatological analysis, and if I understand it right, it excites me as well. I've done a little bit of looking at the effect of temperature on groundwater recharge, and it can be significant, because groundwater recharge is just the leftover part that the plants don't get. And so if the plants are taking more, then that little margin of leftover that gets to the groundwater goes down. And is that what you guys are talking about? Are you guys going to demonstrate that with some calculations, or?
Yeah. So we're gonna incorporate sea level changes with precipitation changes based on some work that I think this is from the GBRAG report. Yeah. So they went in a lot of detail about seasonality of change too.
Right.
Is emission scenarios. So we're
Uh-huh.
gonna essentially use this. I think it does a pretty good job of estimating seasonality changes, and then magnitudes on that in the future. So we're gonna, the 10 scenarios, they're incorporating the known sea level rise, projections with these scenarios, and also we added a piece about simulating a 5-year major drought, perhaps somewhere in the future, maybe 2090 or something. We would reduce precipitation by 30% for 5 or 10 years and see how that affects.
Simulate something,
I think,
something like the 1960s drought that you can see on the left-hand side of this. And I think, I think Peter too, these are questions that the community, the general hydrologic community are trying to answer that, we just don't know, right? Like one thing that we see is that the length of the growing season is getting longer, which, 2-3 more weeks of evapotranspiration can make a big difference in the total water budget. So it's hard to incorporate all these different things, but I think we'll have something to begin with, and we'll I think be able to make some general recommendations. Again, I think the good news on a lot of this is that there's a lot of fresh groundwater moving through that aquifer that keeps that saltwater interface in the bay or close to the bay. So
Dr. Boutt, I think we're going to end on that positive note.
okay, good.
Thank you so much for
the
update.